Good evening, 216ers. This is Professor Kaufman, and what follows is an introductory video to your third project. This project focuses on assembly coding and debugging, and in many ways is simply a rehash of parts of Project 2, but through the lens of assembly instead. As you would look at the project manifest, you'd start to see some familiar characters there. There's a bunch of files that reference the BAT application that involves an embedded sort of battery meter. And what your plan should be is to recreate the magic of your bat update.c file, but this time write it in hand-coded assembly in a file bat update asm.s that you'll need to create. The remaining files are almost literally identical to what were present in Project 2 for this battery file. There's a header file that describes the structs involved, but we'll need to have a little bit more information about those. It's covered in the spec later, and I'll get to that shortly. There's a main function and a little simulator backup function. There's a bunch of tests that are associated, and they're essentially the same tests as were present for the C code because the functionality of the assembly version is going to be identical. The second problem also has a mildly familiar character. There's a puzzle there, but rather than a puzzle box, it's a puzzle bin. And this is provided just as an executable that you'll need to fire up in the debugger. And similar to what you did with Puzzle Box, find some inputs that satisfy the different phases for it. This too has a bunch of phases, fewer of them, and they're worth more credits. It's just that you have no C source code. And so the idea is going to be to use the debugger and put it into the assembly mode and look through the disassembled code there to figure out what's happening. And I'll get us started on that shortly after we get set up for this bat problem. So there's a bunch of information about advisements on how to go about your assembly stuff. Importantly, it is possible to take the C solution that you had for the battery file and run it through GCC to produce assembly code. In most cases, that code, if you submit it, it won't pass muster, so we'll essentially get 0 credit. And this despite maybe passing all the automated tests. In manual inspection, if we seem to detect that, oh, this code really does not look handwritten, it looks like it's machine generated, then we'll just file a big deduction to remove all the credit for your automated tests, and you'll get a 0 on it. So take care to hand code stuff. How might we go about detecting that? Well, hand-coded assembly tends to have a lot of commentary associated with it, and the biggest single piece of advice that past students give to present students in terms of writing assembly is comment the crap out of it. Comment everything, write multiple comments per assembly line if you need to. Make sure that you comment what you're putting in with registers and when you change your mind about that. Make sure to comment why you need to do certain things at certain points. If your code in assembly is utterly lacking comments, this isn't an automatic ding, but it is suspicious because GCC doesn't provide any comments. Use informative label names, make use of the division instruction. All of these things are stuff that the compiler is not going to do for you. And so that end makes it relatively easy to sort out, oh, like this is someone who tried to pass one bias by submitting GCC code and those that don't. Now, this puts folks who didn't necessarily finish up that problem in the previous project at somewhat of a disadvantage. If you didn't actually complete your bat update.c and never got that working, or were dissatisfied because, as you might receive a grade, there's commentary that this is kind of a convoluted, long-winded way to do it and will be hard to convert to assembly, you might be interested in finding out, well, what would a more short, brief, easy to convert to assembly version look like? And in that case, staff will be authorized to, if you meet with them in office hours, provide you, after talking through the solution and the problems with your own, provide you the solution file bat update.c from the previous project. And this can serve then as a template. If you did reasonably well, then don't bother with this. You probably already know what you're doing. But I will make sure that all TAs are informed of this particular edict. It's a little unusual because it involves us giving away part of the solution to a previous project. And that's because we don't want to put folks at a disadvantage for the current project. So with those advisements in hand then, there are a few general cautions about coding assembly that I think are worth reiterating. You may wish to set up an editor if you're using something like VS Code to facilitate more easy editing of assembly, but that's not strictly necessary. That you can get by with MOBA Xterm or gedit, and that is usually sufficient. You want to keep several easy mistakes in mind. For instance, making sure that you use $signs for all your constants so you don't inadvertently go to a raw memory address and go out of bounds. And also keep someplace handy a reference for what the registers are used for in x86-64 conventions. Some of that information is here, and the diagram that we discussed that summarizes a lot of it in lecture, that's present in the specification as well. So maybe keep that one handy. To get started with this, it's a good idea just to get yourself an outline of the functions that are there. And as we set this up, I'll show you how to get this in working order so you can run the test with it quickly, and then point out a few other features. But essentially, this outline that's here is one that you can copy and paste to set up your bat.asm.s file. That's fully intentional and expected. So let's get to the coding part of this for it. I've downloaded over yonder in the CMSC216 directory a copy of the code pack, P3 code. So I'll unzip that. Unzip P3 code.zip. And over here, that should create the directory P3 code. And in here, you'll notice some provided files, including puzzlebin. We'll get to that bugger later. But there is no bat.asm.s or bat update asm.s. I'll have to create that. So one way to do that in my editor is just to find a new file. I'll call it bat.asm. Bat update asm.s. Fire that up. And I will take the code that provides the template here and copy and paste it over here. My editor is set up to edit x86 assembly out of the gates, and so this part has syntax highlighting and some indentation and so forth along the way. Now, this file is not likely to compile out of the gate because for demonstration purposes, it includes some bad syntax here, which we'll have to edit out to get off the ground. For instance, there's a move X here. There is no move X instruction. This will be a move Q or a move B or a move W or something like that. But this is a useful bit of syntax that will be necessary to utilize for the first function. It's the syntax of how to grab something from a global variable and copy its value into a register. And if I had a global variable named some global var, and I happen to know, oh, it's an integer, for instance, that I do a move L of that some global var with a rip offset, and this is something we'll talk about later in lecture, into some register. So maybe I'd move that into RCX or something like that, except that if it's a moves L, it would have to be ECX there. This is actually valid syntax, but I don't want it live right now, so I'm going to comment it out for the moment. Additionally in here are several things worthy of note. You start out in a text section, so this refers to executable assembly, and the function names set bat from ports along with the others, they're set up as global labels here, as well as labeled as global, which means files outside of this single assembly will know about, oh, set bat from ports, that's the thing that's in this file that can be called as a function. Down here, there's a switch over to a data section. Now, what follows is not necessarily an executable bit of code, but rather a spot that you can lay out some global variables. This one's called myint, this one's called otherint, and then there's a myArray down here. You can see that there's something we'll talk a little bit more about tomorrow in assembly, I think, that you can use these directives .int to say, at this location, I'd like to put a value, 1, 2, 3, 4. It's an integer value. I can also specify that in binary, which turns out to be useful in this project. Or if I say, here's a label and several ints, it amounts to like, oh, starting at this spot, there's an int followed by another int followed by another int. And this constitutes then more or less an array. Now, I'd suggest against using these particular names for things, myint, otherint, myArray, those stock ones, but it's in all likelihood that you'll need some sort of an array of little bit masks if you're going to reflect the structure of the C code that you wrote for one of the functions, the second function later on. And speaking of that second function, we'll switch back into text mode here. Don't forget that. It'll lead to really weird errors otherwise. And then down here is the start of that set display from BAT, along with some syntax to say, oh, if I had something called myArray that's up here, this same RIP-based syntax will allow me to load up the address, the starting address of the array, into a register RDX if you wanted to, for instance, access elements of that over there. Finally, then there's one last function, the bat update function here. And you can see all of these, they're just fragments. They don't contain anything. And so at a minimum, we're probably going to want to, in order to be compilable and testable, fill in some rough definitions for those things. And here's how we'll go about doing that. Up top, the set bats from ports. I'm just going to plop down a move L0 into EAX because that's where the return for this function should go, and then I'll return. And I'm actually just going to copy that stuff and paste it over here. I don't really want to do these things because I'm not sure about them yet, but I want to do essentially the same thing here for bat update. If you check the function prototypes for these, this one returns an int, the second function returns an int, and the third function returns an int. So we've essentially set up the bare minimum of whoever's calling the function is going to set up the arguments, and now in the code itself, we've set up the return values for that, 0 in each case. So at this stage, it's probably worthwhile just to give it a whirl and see if it compiles. Let's see, need to change into P3 code here. And you can see here, I've got my bat update asm.s, and the little tilde file is the backup file that Emacs creates for this and helps me to recover if I lose something. But I should be able to do a make at this point, which will compile everything. And lo and behold, it compiled out of the gate. If, for instance, you forget to uncomment something like this with this movex, then you're liable to get some compilation errors that says there's no such instruction as a move x over there. And so be advised that will stand in your way. But this sort of minimal bit right over here is all that's needed to get started and run the test. So I can do a make test prob1 now. And this will spit back probably a lot of failures at the moment because, my code isn't doing anything. But hey, being able to run the tests and see what the results are that's better than not being able to run the tests. So it's a good start. And if I really wanted to, I'd make this just a bit bigger so that you could see them things line up over here. All right, so that's not a bad start. Now, how do you actually go about coding these functions? Well, there's some details about that show up in the implementation notes for each of these, along with a reminder of what the function is about and supposed to do. And you may want to review some of the C notes on this as well. There's some advisements about what will be special about this in assembly. For instance, this first function is responsible for grabbing out some stuff from global variables and then looking at that stuff and plopping down certain values in a bat t struct that's passed in via a pointer there. So the only argument to this thing is a pointer to this bat t struct. There's instructions here about syntax to use with assembly in order to access the values that are present in global variables. And so make use of that in various ways to copy stuff into registers and then start poking around in that stuff. As you would figure out, oh, this is the value that I need to plop down in the battery millivolts over there, then you need to know precisely where that is with respect to a pointer to it. So the millivolts fields, if you look at the structure definition, is the first one in there. It's a 2-byte short. And so this table indicates it'll be 0 bytes away from the start of the structure. And so a syntax that looks like this of move a 5, 0 bytes off of some register that points where this thing is at. This is all it takes to plop a 5 down in the millivolts field. Now, you'll have to decide what register it is, and hint, hint, it's the first argument to this function, and so just figure out what register holds that in it. Later on, as you would need to move things into percent and mode, then there are similar syntaxes here, it's just that they're an offset over here. Now, there's no reason that looking at a struct definition, you'd be able to necessarily guess, oh, this is where it's going to be 0 bytes off, or 2 bytes off, or 3 bytes off. You might have some suspicions, but oftentimes the compiler makes decisions about this on your behalf, and so you'd want to look carefully at the output of the compiler, oftentimes in the form of generated assembly instructions to see what those offsets are. But I've given you the table here in terms of if you have a pointer to a bat t struct, this is all you'll need in order to modify those values. Again, you may want to look at some recent discussion exercises. For instance, last week's discussion on the coins T struct did very similar things. And so that should serve as training and inspiration for how to get the job done in this case. Have a look back at that, and I'll post a solution to it in short order here so that folks can look at that solution if they're still in doubt about the stuff. Set display from bat is going to arrange for taking in this bat T struct and then setting this pointer to a display to be a bit pattern that reflects, this is how I'll display a 1, this is how I'll display a 5, etc., to reflect the voltage or the percentage full things are there. Now, if you look carefully, you see this is slightly different than the first function. Here we're getting an actual struct versus in the first function, we're going to pointer to a struct. The equivalent in C would be I'd use arrows here, but since it's an actual struct here, I'm going to use a dot. In assembly, this appears even more different in that the struct itself, this bat T that's up here, it's going to be packed into the single first register argument. As you'd want to extract the individual fields of that struct, you'll have to make use of some shift instructions to pull out the millivolts individually, pull out the percent individually, pull out the mode individually. And if you're tracking, the second functions you wrote on coins T in last week's discussion did exactly this. It said, oh, there's a coins T struct that's coming in. It's packed into a single register. And so to extract the quarters, nickels, dimes, and pennies, I have to use a series of shifts and masks in order to get those fields in individual registers. That's exactly the same set of techniques to have here. So look back at your solution and just adapt based on where in the struct or where in the register the individual struct fields are and how big they are. Finally, then, as you'd want to create this bit pattern, it's useful to have a series of bit patterns in an array, perhaps a global array in a data section above this function here. So some additional advice on how to set that up is over here, and you're free to use the GCC honored syntax to state some binary sort of binary immediate values there rather than the decimal values there. If you load up then the address of that array, you can make use of it to start combining, shifting, and ORing bits together using assembly instructions. And if you can't remember what are the shift instructions, then look that up in a reference manual. For instance, the Brown University's X64 cheat sheet has instructions on where to find those shift and OR instructions. The final function down here, bat update, is interesting in that, unlike the first two, which basically get control, they do a bunch of operations, and then return. They don't call any other functions, and so themselves are leaf functions. The last one is a little different, as in bat date is supposed to call the previous two functions. And to that end, you'll have to be subject to all the worrisome issues associated with calling functions. If they need to be passed an argument, then you'll need to set up those arguments. If the argument has to be an address someplace in the stack, then you'll have to arrange for that. You have to align the stack associated with proper 16-byte divisible boundaries in x86-64. So there's a bunch of advice and review information about this here, but keep close at hand this notion of the function call semantics associated with that stuff and make use of that there. We try as much as possible to assign partial credit, but it is true that, for instance, this last function, since it's dependent on the first two functions, the set bat from ports and set display from bat, it's hard to get this last function correct unless you've actually finished effectively and gotten correct answers for the first few. So in most cases, we won't necessarily be able to award partial credit for that stuff. Okay, the second problem then is very much like the puzzle bin before, except that, puzzle box before, except puzzle bin in this case is all binary. And to show you what that more or less means, let me pull up this over here. What kind of a file is puzzle bin? It is an L64-bit executable. I can run it out of the gate. There's no compilation necessary. It's just that I have to provide an input file. If you look at the provided input.txt, you'll see it's your directory ID, etc. And so to that end, I could run it on that. So use puzzle bin on input.txt, and I, of course, need to adjust this directory ID. So let's plop down prof k here. And the remaining line here is the first input to this, but we'll need to sort of modify that shortly here. And as you'd run this after modification, then you see prof k, and that's no credit out of the gate. So there's not much to look at here with this thing, because if you pull this up in your text editor, here's puzzle bin, you'll see a bunch of gobbledygook, because this is compiled binary. That shouldn't intimidate you overly, because you're equipped now with GDB, and so it shouldn't come as a great surprise. Just fire up GDB. I'll put it in TUI mode, the text user interface. And at this stage, I have to download some debug information. I have no source available, but I can change the layout to assembly mode, which will show me the instructions in a decompiled form. Now, don't be too intimidated here. This decompiled form lacks all of the suffixes, but that's not of great import. In most cases, you can infer, oh, if this is pushing with 64-bit registers, it's a push Q. If it's someplace else down here doing something with EAX, then this is a 32-bit move L here. But this is more or less how you're going to have to operate in terms of working through this main function. The basic structure is the same as in, oh, there's phase 7 and phase 6 and so forth. That's up here in assembly. I find it actually sort of irritating that the GDB only lets me look at a little narrow window of this at one time. So I'm actually going to press Control Z for a minute to suspend this and make use of our good friend object dump to disassemble this. So here's puzzle bin. And at this stage, if I punch enter, then you'll see a lot of text flow by, because this is the output of disassembling that entire binary and spitting it out to the screen. I could, scroll back and sort of poke around on stuff, but if you get hip to Unix tricks, oh, anything that gets printed to the screen, I could redirect to go into a file. So let me call this puzzlebin.asm. Well, let me call it .s because it'll be easier. I spelled it wrong, but no matter. Let me just rename this because it'll bug me otherwise. And yeah, I still haven't spelled it quite right. All right. So this is that output, and is handy then to be able to look at in a text editor, because it allows you a little bit more global perspective on what's in here. There's a lot of stuff. This is a so-called statically compiled binary, so that it includes and is self-contained all of the things like printf and stuff that would need to operate. If I buzz around and find where's that main function at, main plus, for instance, somewhere around here, find main plus. Okay. Here it is. Okay. Okay. Wait. It shows a little bit differently than it does in the debugger. So here's my main routine. And you see structurally, if I look down just a little ways here, you get into a series of calls to phase 1, phase 2, phase 3, phase 4, etc. Essentially, all that's going to happen in between these is to add something on to your score, which is in a global variable here. You can even see some hints here that's given in the GDB commentary about what that thing is. So most of the action in this case is going to be in these phase functions. And an easy way to sort of get started is, set a breakpoint at phase 1 and have add it there. So I'll do that now by bringing back up the debugger. I'll probably want to show the registers here. Regis. So once I start running there, I'll set a break at phase 01, and then away we go. Let's see. Sorry, I'll probably want to set args to input.txt, and that'll be able to run. Okay. So running there. So here we are in phase 1. And you can see there's some preamble here of doing some stuff with EAX and calling next line and whatever PB rand is, no matter on that account. So we're not going to quite bother with any of this stuff here. But one interesting thing you might want to sort of fish out right away is like, oh, next line here. When that function is called, like all functions, its return is going to be in RAX. And you can see immediately RAX is being copied someplace. So I may as well look at, oh, that's changed. Like, what is RAX? Looks here like, okay, it's a big integer. But this might be a memory address of some kind. Lines are oftentimes texts. And so I'll sort of infer like, okay, what if I were to print as a string what RAX is? Oh, sorry. I'll have to examine what it is at that spot. Oh, okay. And this is giving me a hint like this is actually a known location. It's some distance off of where inputs is at, where it's some global variable. And it's 1, 2, 3. And that matches up with our first input line, 1, 2, 3. So apparently this first one is reading the first line as 1, 2, 3. And to that end, like no great surprises there. So I might start just stepping through a little bit and seeing, okay, there's a PB rand here. We know that'll come out as RAX, so maybe I'd want to look. Oh, actually, I looked at it here. It is 25,169. Well, it's not particularly useful, but no matter. So let's keep stepping and see what else we can see here. Oh, interesting. Okay, there's a division instruction here. It's dividing by something called quote count, and then there's something called quotes over here. All right. Well, if I keep moving along here, let's see. Then I get to this spot, and there's some sort of a test. And JNE to 01. Ooh, okay, this looks bad, because this looks like I'm about to hit a failure here. So that was no good, really. Probably not going to want to go into this failure routine. If I continued at this point, then yeah, failure. Okay, so that wasn't, I would credit right. Okay, so let's give it another shot and see if we can pick up on a few other things. At least we know where our line number went. I'm interested here in, there's something being done. Let's see. When I was jumping to that failure, I guess I went too far again. Okay, so this is looking like, okay, JNE to phase 63, it's here. Oh, okay. Actually, at this spot, JNE, that's a jump not equal for whatever this thing is. And if I don't take this branch, I'm not going to go into failure. I'll instead return out of phase 1. So it looks like to me what I want to happen is to not take this branch. That whatever equality this test instruction that was given, I want it to be equal. And EAX here, that's set as an whatever this call is here, this mysterious call. That's after that. Don't know what that is, but we can at least look at because I can see, oh, RBX is moving into RDI. Something's getting moved in RSI. So this is like 2 arguments to some function here. It's an unnamed function, but no matter on that account. Okay, so let me back up quick. I'm going to set a breakpoint here right before this call. And here's where it'd be useful to know a few things about working in assembly. If I want to set a breakpoint here at this line, there's a special syntax for this that's given in the GDB guide. There's a whole section in here specifically on debugging binaries. If it'll ever load up. It's down here, debugging assembly in GDB. And if you, it's actually up here in this sort of extended breakpoint stuff. So here as you'd have some function with an offset associated with it that you wanted to make use of, then the syntax is to break a star, the function name, and then the offset that's there. So let me bop back over here, and so I'll break the star for phase 0, 1, and this is at plus 52, whatever that compare is doing. Okay, so if I were to examine now, I need to run from the beginning, and then I'll just continue at this point because that'll get me down to this spot that's right before this call, whatever that is. I've loaded up RDI and RSI so we can at least look at what the arguments to this function are. I will examine RSI. Oh, okay. Well, this is interesting. And I pot shot that. Is it a string, perhaps? That's actually good. RDI, I'm thinking, is probably an input line. Oh, yeah. Okay. This is the 1, 2, 3 in here. All right. So 2 strings walk into an function, and some value comes out of it. What are we thinking? Maybe string comparison here? I mean, I could have done you some more favors by not omitting the function name here, but that seems fair. Now, clearly, these 2 strings, an Android black hole and a glass of milk, want to a bar, it is not equal to 1, 2, 3. So if this really is a string comparison function, then what we'll expect as it comes out from this test is something that's non-zero, because like a standard stir comp, that's going to compare 2 strings and turn 0. But there are 0 difference between them if they're actually equal. Okay, so I'll next instruction that and see over here that, yeah, indeed, RAX is quite a large value. It's not definitely out there. So on a test, it will sign that, yeah, there's some non-zero bits in there, and I'll jump not equal away from that. So as a pot shot, here's my inputs. Let me try to grab that out here. My terminal's being a little turd, and it's not actually allowing me to select this thing here. Let's just copy it. We'll brute force it here. So instead of 1, 2, 3, I'll move that down, and Android, a black hole and a glass of milk. Walk. Let's see. Can I get a little more there? It was RSI. Walk into a bar. Let's see. Walk into a bar. And I think that's no period there. Okay, so let's see if we can get a match on that. Now that I've got new input, I'm going to run. And I'll just continue at this point because I want to get back to this spot and see that I get the right input for this. So print, examine as a string RSI and examine as a string RDI. Let's see, they look to be about equal. So let's see if we've convinced the string comparison. REX says not so much. Okay. Oh, shoot, I misspelled it here. Rather. My bad. You probably all saw that as the little red line went up, but no matter. Okay, give it another run. Continue up to this breakpoint, to next instruction, and still no dice. Okay, that's bothersome. Did I save everything? Okay, yep, and I reran from the beginning, so it should have reloaded. Let me print out those values once more. Let's print on and RDI, Android, a black hole, and a glass of milk walk into a bar. They look like they're okay, but I'm going to step anyway and sort of see. Yeah, I'm about to fail. So, okay, this is perplexing. I'm going to pause for a second and just see if I'm copying the string wrong, and that's the trouble with it. Actually, I'll just demonstrate how to do this. So, my terminal is acting a little bit weird because I can't copy things in this mode. I can disable the TUI, though. And this gets me the sort of more traditional command line mode for GDB. All the same commands are still available, so I could examine the RDI and examine RSI here. And in this sort of normal terminal mode, I can grab it out. This is the string that's the target, and I'm super curious now. I'll copy this and paste it here. I didn't capitalize the A in Android. What a doofus. Okay, so that should get us back in shape here. When I re-enable the TUI with TUI enable, this will go back into this mode. I'll give it a run. Yep, and I'll continue here, maybe step, say next instruction it, and still we are not equal. Well, this is just frustrating as all get out here. I'm going to pause for a second and see what I'm doing wrong here. Okay, well, I feel silly because it was uncapitalized. I was just confusing the inputs versus the expected there. So in terms of this, it was just a misspelling, which is encouragement to all of you to copy those directly from the terminal as you'd see it and paste it into your input file rather than wasting time like I did trying to type it out and so forth. One interesting way that you might look around for that is, for instance, to jump over to the disassembled stuff over here and see if there's any string data in here that can pull out. And I'm not seeing any. But if you zip out over into the terminal, there are a few other handy utilities for diagnosing binaries. One of them that's interesting is called the strings utility. This one will just look for what looks to be ASCII strings within the binary and spit those out. And you can see as I would run that on the binary, I got a bunch of output as well. And so I'll only put that into puzzle bin strings .txt. And then I can pull that up in my text editor here. And maybe search for, hey, here's Android. And there's also a whole bunch of other stuff that's in here. So this is one way then to make it a little bit easier to copy strings around if you're not working in the terminal. So now I've got my this thing compared favorably. The test here is going to fail because there are no 0 bits set after the return from that string comparison. Let's see. So I'll next here, and this is going to get me out of the first phase and score me a few points. To demonstrate, here's now if I ran puzzle bin on input.txt, I've got myself 5 points here. Phase 2 is falling down, so the right approach would probably be to break. Actually, I'll delete my other breakpoints. Delete everything, and then break at phase 02 instead. Now I'll give this a run and see how we're doing. In terms of input lines, I have right now 1, 2, 3 again for the input for phase 2. So hopefully, we'll see something about like what that's in there. There's a bunch of junk here that I guess might matter, but I don't care too much about it because our first input is read here at next line. So if I move forwards on this thing, we're good there. And in terms of just scanning up ahead, I can see the next interesting thing that's done is probably this call to ISO C99S scanf. Well, a little hint here. The ISO C99, like, there's no reason you need to know that, but scanf, this is something that should smack just of a little bit of familiarity to you. And the particular variant here, scanf, that's one that you would want to look up potentially. A good spot to look it up is to suspend the debugger for a second by calling FG or by pressing Control Z. We can bring it back later with FG, but right now I actually want to use the terminal just to say man scanf. This will pull up the manual entry for the scanf function. And you can see over here, this is a standard C function. There's a description for it down here. The essence of it is that it's like scanf, wherein scanf reads some kind of inputs and then will fish out integers and strings and floating point numbers and so forth according to a format specifier. It's just that scanf is targeted at reading not from typed inputs, but from strings. And so the first thing that goes in is a character string. And then the second thing that goes in is a format specifier that specifies what to look for in this string, what to fish out from it. So that's interesting and useful. The fact that there are 2 arguments going into this scanf function will make, or at least 2, I should say, will make me want to look around for how are the arguments getting loaded up into scanf here. And you can see, oh, actually the instruction I'm on right now is going to move something into RDI. That would be the first argument. and then something else into RCX and RDX. That's a third argument, and RSI. Third argument, fourth argument, second argument. And so if I'm looking just at the first two, maybe I'll set a breakpoint here at this phase 02 plus 48. That's where the call is at. I'm just going to continue up to that point. So at this point, any arguments that are associated with this thing should be available now. So let's have a look. According to that C documentation we saw against a moment ago, the first two arguments in RDI and RSI, those should be strings. So let's have a look at them. I can see up here RDI is some, looks like maybe a memory address. RSI also looks like it could be a memory address, although it's some distance away. There's certainly large decimal values, so no matter on that account. Let's examine RDI. That is 1, 2, 3. Okay, so that's my inputs. It's the string that's being read here. And if I examine as a string RSI, hey, that's a %D. So that would lead one to conclude that in this part, there needs to be at least two integers that are going to come in this, and they'll be read in as 1 and 2 here. Now, where they read to is probably going to be pertain to additional arguments, because in a scanf style function, you say where to read from, and in this case, it'll be from a string, what to read, in this case, 2 integers, and where to put what's read. And you can see here the next couple arguments that are set up, RCX and RDX, they're stack locations. The stack pointer is copied into RCX, so that must be where the first thing that's being read is going to be located. And then 4 bytes off of the stack pointer, this is getting loaded into RDX. And so that'll be where this second thing is. Let's verify that. So I'm not going to bother to step through scanf. Instead, I'm just going to step over it with the next instruction. You can see that RAX was 2 here. That's the return value from scanf. And as we discussed before, most scanf functions, they return how many things were actually read among those that were specified with the %Ds over here. So that's a useful thing to sort of realize. We're going to compare this EAX return value against 1, and it's less than or equal to 1, jump someplace else. Maybe let's just scan ahead a little bit here. Rats, I lost control of let me try TUI disable, and oh, TUI's mad. Oh, crap. Okay, I'm going to pop out of this and bring it back. TUI enable. This was make me... Okay, good. Okay, I wanted to scan ahead to this 152. It's going to be down a little ways. And just see what's going on down there. Is that someplace you want? No, it's definitely not someplace I want to go. It's a failure. So we're hoping not to take that jump here. And it looks like we won't because there's a 2 up here. And that's not going to compare less than or equal. So let's just move ahead a couple there. Cool. Okay. So now we're picking up stuff up off the stack. And since those were arguments that were going at scanf, RCX and RDX here, stack location at the top and 4 bytes off the stack, that stands to reason that maybe this is where some of those values that were read are plopped down. And so that would mean if I move what's in at the top of the stack into EAX, this is probably going to be one of the 2 values, 1 or 2, that was in the string that was getting read in. So if I move to the next instruction, EAX has a 2 in it, so it's unchanged, but it had a 2 before. And then that's going to compare against 4 off of RSP. So let's just look check. Let's examine what's at the stack pointer. It's not %, but $RSP. There's a \002. If I said show that to me as a decimal, it's 2. And if I said RSP plus 4, there's a 1 there. Okay, so that makes sense. That this upper location, that's where the 1 went, and this somewhat lower location, that's where the 2 went. And it looks like they're getting compared here. So that should be enough right now to move you forwards a little bit on this. What exactly is done with these, that hasn't been revealed in my demo here, but this has revealed a whole bunch of things about how to move and act in here, as well as helping you to solve the first phase without too much trouble, which is essentially find the string that's looked up based on your unique hash code that's coming from your directory ID, and then match that string against it. And in the second phase, you're going to need at least a couple numbers. The use of scanf will show up later on to parse out additional stuff. So have a look at that and make sure you're prepared to sort of look at those format strings to figure out how many things are needed in each stage. That'll do me for now, and I look forward to seeing all of you make your way through this puzzling endeavor. If you look around, there's a related assignment called the binary bomb. That's actually one that's a classic that's been running for about 20 years that the textbook authors, Brown and Halloran, put together. This is a variation on that that's somewhat less intense to set up because it doesn't involve a sort of server that communicates with your programs. But it's similar in spirit. And so if you look around for tutorials on how to solve the binary bomb, this may prove useful and give you some tips about how to proceed. Although this being a home-rolled endeavor, it'll look a little bit different than what that official assignment looks like. All right, I'll see you all in lecture tomorrow, and happy hacking until then.